All right, guys. Now we're going to talk very briefly about a process called steganography. Steganography sounds really cool, right? It's one of the coolest names I think of any process that we learn about in this class. But it's essentially it's the process of hiding information within other information. So you get one piece of data and you don't even realize that there's a hidden message inside that original message. This is a good example of that, okay? So this is from the National Weather Service in Anchorage, Alaska, and they're sending out a message about the weather in Anchorage, Alaska, but this came out during one of the recent government shutdowns. And so none of these people were getting paid, even though they were still working for the National Weather Service. So they send out this long message about all the different, the weather all around the Anchorage, Alaska area. But hidden within this larger message, there's this. If you read the first letter of each line, it says, please pay us, i.e. they're sending a hidden message within their weather bulletin about that government shutdown and how upset they were about it. So that's essentially what steganography is. It's taking a small message, like please pay us, and hiding it within this larger message so that a normal observer, without this green box, a normal observer wouldn't be able to read that hidden message. They would only see the larger message. So that's a fairly simple example, but it's a good example of how this process works. There are lots of different ways to do this. Everything from hiding a text message within a larger text document, like on the last slide, to hiding things in images, to hiding things in MP3 files, to hiding things in lots of any kind of digital data can have some kind of steganographic data hidden within it. Some process of doing that hiding are more complicated than others. So putting, the first letter of every line in a text document, that's a very, very simple way to do it. And I'm going to talk to you about another way to do it, which is also very, very simple, but slightly more complicated and gives you another idea of how this can be done with specifically digital data rather than text. Okay? This is called the least significant bit method. So if you'll notice, any given computer image is made up of pixels, and each pixel is a solid color. So if you were to zoom in on your computer screen right now, you would see that there's millions and millions of pixels that make up the image of this video. And in fact, you can tell kind of right here that my green screen isn't working very well, and a lot of these pixels are flashing from color to color, which is what causes these little flashy dots up here in the thing, and which I apologize for. I don't have the best camera and green screen setup in the world, but I'm a teacher. I don't get paid much. So those are pixels, right? So we've zoomed way in on this image, and it's just a 4-pixel image. There's red, black, yellow, and blue. Okay? Now, in reality, there's a billion different shades of red, but we've chosen the reddest red. And there's different shades of yellow, but we've chosen just the most basic form of yellow. Each one of these pixels is kind of assigned a digital name. Okay, so this color red, that is the binary code for that color red. So when your picture is saved on your hard drive, it's saved obviously as a giant sequence of ones and zeros, right? Each pixel gets assigned a color, and those numbers are put into order, and then when the computer is trying to recreate that image, it just pulls out, these ones and zeros for this pixel correspond to this particular shade of this particular color, so I'm going to display that in that pixel. Next pixel, what particular ones and zeros are there? Oh, well, that ones and zero code corresponds to this particular shade of this particular color, so that picture gets that color. And this is kind of how it looks, right? So red has this binary code, black has this binary code, yellow has this binary code, and blue has this binary code. Okay? So what's important here, though, is as the digits go from the left to the right, those digits become less and less important, okay? So for this red pixel, if we were to change this first 1 to a 0, it would radically change the color of this pixel. You would be able to tell what the difference in color is. But as we move over here, these numbers become less and less and less important, and more about finding fine, very specific shades of red, okay? So if we change this 1 to a 0, this red color would shift to a very, very slightly different shade of red, but it would be such a small change as to basically be indistinguishable. The human eye would not notice the difference if we changed this 1 to a 0. If we changed this 1 to a 0, big difference, people would notice. Changing this 1 to a 0, so small, nobody really is going to notice anything. So, as such, let's go in and change the last 2 digits of each of these 3 numbers to something else. We're going to hide our message in there. And by changing the last 2 digits of these 3 numbers, we've now hidden 6 bits of information in 1 pixel worth of data storage. And we've changed the color of that red, but we've changed it ever so slightly so that the human eye is never going to notice the difference, right? Now we'll do that with all the pixels in this image. So 6 bits of information here, 6 bits of information here, 6 bits of information here. And now we have 6, 12, 18, 24 bits of information hidden within this 4 pixel image. And it's changing it ever so slightly, but nobody's going to notice using the human eye that those colors are slightly off. So once we've hidden that data, we've hidden 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, you know, so we read it like this: down, 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 down. Now, those 24 bits of information combine, once we put them in order, by the way we want to read them, into the letters C, A, and T. So now, using 24 bits of information from this 4 pixel image, we've modified it and we've changed the colors ever so slightly, but we've hidden a secret message within these 4 pixels that is this 3-letter word. And if we tried to hide it in these numbers over here on the left, it would have changed the colors dramatically. But because we're using the least significant bit, i.e. those numbers over here on the right, we're changing those, it's not changing the image basically at all. The human eye cannot tell the difference between this image and this image, even though they're very slightly different. Okay? This red is very different than this red. This black is slightly different than this black. But we don't notice. And now we've hidden this message within the pixels of this image. So now blow it up to a picture with 1 million pixels or 10 million pixels or 100 million pixels, and we can hide a lot of data within that many pixels without changing the image in any significant way. So here's an example of that. This image of a tree has a steganographically hidden image within it, okay? Using that least significant bit method we talked about in the last slide, they hid this image inside that one. And anybody looking at this image would not know it had any hidden message within it unless they knew to look there. So this is how a lot of terrorists communicate. So Al-Qaeda, if Al-Qaeda wants to send a message to one of their cells in the United States, they don't call them on the phone, they don't send them an email. Those things are too easily tracked. Even if they're encrypted, even if we can't break their encryption, we can still tell who they're talking to, and they don't want that to happen. So what they do is they take a picture of a training camp or take a picture of whatever they want, and then steganographically hide a message to their cell within that image, and then just post the image on Twitter or on their own website, or throw it on Facebook or whatever. And at that point, tens of thousands or millions of people are going to view that image. But only a teeny tiny number, even as low as 1 or 2 people, might be able to extract out that steganographic message that's hidden within that image. Now the FBI is trying to figure out who even if the FBI can figure out, hey, that image has a steganographic message embedded within it, they might not be able to figure out what that message is, and they can't even figure out who that message was sent to, because again, tens of thousands of people have looked at the image and they have no idea who the 1 or 2 people who are receiving that steganographic message are out of those tens of thousands or millions of people who viewed the image. So it's a great way to hide data that's very similar process to encryption, but different. So that is the end of our third technical thing, and we're going to come back with the fourth one. I'll see you then.